Is on solving symbolically, which means we're going to learn how to solve problems using algebraic symbols first before we plug in our numbers, and that can lead us to some important insights which it's hard to get if we rush to trying to calculate things with numbers right away. Our objectives are you should be able to solve a physics problem using a symbolic solution procedure, which I will step through, and derive functions of unknown variables in terms of known variables and constants, and we'll see some very good reasons to be able to do that shortly. So solving symbolically. This is a great procedure for tackling any sort of physics problem. Number one, list all relevant information as knowns. This includes drawing any diagrams if necessary, if you need to do a free body diagram, or maybe just sketch the problem so that you know what's going on. Often a visual can help us understand key insights about the problem that just reading something wouldn't be able to do. Step two, identify relevant theories, laws, and relationships between variables. This makes us stop and think, hey, wait a minute, what kind of a problem is this? What is the knowledge that I'm going to have to use to solve the problem? And that could come in the form of equations, or it might just come in the form of principles. Problem solving isn't always about rushing to an equation and then trying to plug values in. Sometimes we just want to figure out, well, what are the principles at play here? Is there a scientific principle of value that can help me figure out what's going on? Now, number three I put in bold because this is going to be the part that we practice the most in this lesson. Using algebraic operations to express the unknown variables of interest in terms of known variables and constants. So that basically means that on the left-hand side, I'm going to abbreviate that LHS. I want to have what I'm looking for. What I'm looking for. And on the right-hand side, I'm going to abbreviate that RHS. I want everything else. And preferably that is going to be stuff that is known. Now, sometimes we're going to be asked to find some variable as a function of another variable, and then maybe we don't know everything on the right-hand side. But in general, it's nice to be able to put everything known on the right-hand side so that when we end up solving the problem numerically, we end up plugging in values, then all we have to do is plug in known values, crunch through it, and solve. And then that's really the easy part for most people. And then we plug in known values and calculate. Step four is the fun part. That's when we kind of know what's going on already, and we can plug in some numbers and just crunch through. And it's kind of satisfying to be able to crunch through the problem. So there's some advantages to symbolic solving. Why do you want to do this step instead of just jumping to solving? Well, the main reason is that relationships between the variables can be evaluated analytically. So, and what I mean by relationships is, well, how does string tension relate to wave speed? If we were to lay out the equation for that, we could see symbolically what the relationship between them is. And this is going to tell us a lot about these variables and the relationship between them. That's really actually hard to see if we rushed to finding the numerical answer. The second reason is it allows us to do a sanity check before we go through the work of calculation. We can take a look and say, hey, does this even make sense? Should these variables be related the way that my equation is saying that they're related? And if not, then maybe I did something wrong in my setup. Maybe there's a fundamental misunderstanding of what I have here. Key flags for symbolic solving. If you ever see these phrases, express x as a function of y and z, or find x in terms of y and z, it's asking you to put x, whatever it is, could be velocity, could be temperature, could be tension, could be wave speed, whatever the variable is, you want that on the left-hand side of your equation, and you're going to want to put these other things on the other side of that sentence on the right-hand side of the equation. And if we can structure our equation algebraically to have that structure, what we want to find on the left-hand side and everything else on the right-hand side, then it makes a lot of things much easier for us. Okay, so let's see our method in action. Okay, example 1. An object with a mass of 5 kilograms is being pulled across a surface with a force of 50 newtons. The force of kinetic friction between the object and the surface is 30 newtons. Find the acceleration of the object. Now, this is a pretty straightforward Newton's laws problem. If you've taken introductory physics before, this is fairly typical of what you might find in the dynamics unit. But let's go through this as an example of our solution procedure. So step 1, I want to write my notes. And this is always a good habit. What do I actually know about this scenario? I have an object, the mass is 5 kilograms, so I'm going to write it using my variables. And I'm going to include units as well. That way, if I have to convert units later on, then I know what units I recorded these values in, and I'm not going to just plug in random numbers. Let's see, pulled across the surface with a force of 50 newtons. That is an applied force. We'll just call it FA, is 50 newtons. The force of kinetic friction between the object and the surface is 30 newtons. So we can list that as FK is 30 newtons. Great. And we are looking for the acceleration of the object. So I'm also going to make a note of that so that I know what I'm looking for. If I ever forget, I can do eyes on the prize and say, what am I looking for? I'm looking for acceleration. Okay, next thing I want to do is draw any diagrams that might help me. And as good physics students, we know that any force problem, the diagram that helps us is going to be a free body diagram. So I'm going to draw my object here on a surface. I know that the object has mass, therefore it has weight, and it's sitting on that surface presumably, so any object touching a surface receives a normal force from that surface. The object is being pulled, and it's being resisted by kinetic friction. So I'm going to put that in the other direction, FK. So there's a diagram that gives me a visual depiction of the forces acting on this object. So far, so good. This shouldn't be anything new. Okay, so next step is I'm going to write down some principles that apply. And let me make a little line here so I have some room. And let's write principles. Well, anytime I have a force problem, I know I'm probably going to be dealing with Newton's laws of motion. And according to Newton's first law of motion, the net force is going to be the sum of the forces on the object. And it seems like the horizontal direction is what matters here, so I'm actually just going to make a statement that the net force on this object is going to be the applied force minus the frictional force. They're in opposite directions, so they should have opposite signs. That's just going to be my statement. I know that from Newton's first law. My second principle that applies is Newton's second law. I know that the net force is equal to the mass of the object times the acceleration. So I've made two statements here using mathematical language. I've made a statement using equations. And this is going to allow me to do some things that I wouldn't be able to do if I just jumped right in and started solving with numbers. Now, if you recall, my third step was to use algebraic operations to express the unknown variable of interest in terms of known variables and constants. And that meant left-hand side what I'm looking for, and right-hand side everything else, everything that is known. So if I apply that here to this problem, well, I ask myself, what am I looking for? I'm looking for the acceleration. So I'm going to put acceleration on the left-hand side. I can get acceleration by itself if I divide Newton's second law all the way through by mass. So it's divide by mass, divide by mass. I get to cancel those out, and I'm going to end up with the acceleration equals the net force divided by the mass. Now the thing is, I don't know the net force yet either, but I do have a statement up here, a statement from Newton's first law that lets me put the net force in terms of known things. I do know what the applied force is, and I do know what the frictional force is. So if I'm trying to put only knowns on the right-hand side of the equation, I've got to keep on substituting. I'm going to substitute in for the net force. So acceleration equals applied force minus kinetic friction over the mass. Okay, now I have put what I want to find. This is my unknown of interest, is right there. It's the acceleration. And notice that everything on the right-hand side is known. Every single thing on the right-hand side of my equation is a known. I don't have anything that is an unknown. If I had left it up here as just F net, this is not yet known. This is an unknown as well. So I'm not quite done yet. I want to put everything in terms of knowns only. And now that I have everything in terms of knowns, I can stop here and pause before I plug in some values and just ask myself, what does this even mean? I have on the numerator, I know that if the numerator increases on this side, the value over here should increase. So if the applied force minus friction increases, I should get more acceleration. I know that if I increase the mass over here, the denominator is going to increase, which means this whole fraction decreases and I should get less acceleration. So already I can tell some relationships between variables and I don't need any numbers. If I want to increase the acceleration, I could increase the applied force. I could decrease the friction, lower the amount that it's being reduced by up on the top, because this is a negative. Or I could decrease the mass and reduce the number that's in the denominator. So there's three ways I can see to increase the acceleration just by looking at my equation when I've solved it in this fashion. So this is something great, and this is our goal, to have what we're looking for on the left side and only known variables on the right hand side. Once we've done that, then it makes sense, then it's okay to jump to calculate. So I'm gonna substitute in known values from my known list. I know that the applied force is 50, the frictional force is 30, and the mass is 5. Now here's the fun part. I just plug in known values, 50 minus 30 over 5. I simplify it. It's going to give me 20 over 5, which is 4 meters per second squared. And this is an answer that I can box. I've solved the problem with the numerical answer, but really what gives me the understanding is right here. Okay, the numbers, that's just math. The math is not the physics. The physics is right here, being able to tell the relationship between different parameters. Certainly math is a tool, but it's not really the main point. Okay, that's an example of how we should solve problems. Knowns, diagrams, a list of principles or equations. I could have written these out, by the way. I could have made a statement. The net force on an object is the sum of forces, if I wanted to do it in words and not an equation. Then I substitute values, use algebra until I can find the unknown on the left-hand side and nothing but known values on the right-hand side. And then only at the very end do I do my last step of plugging in numbers and solving. So let's do some examples of just trying to find functions of one variable in terms of other variables symbolically. Here's an example. What I'd like you to do is pause the video and try and solve for VI in terms of VF, A, and D. So we're trying to find the initial velocity in terms of the final velocity, acceleration, and the distance. Ready, set, go. Did you do it? I hope so. Let's check. So if I want to get VI by itself, the first thing I need to do is get this term off to the other side. So I'm going to subtract 2AD from both sides. So I can get a VI squared equals VF squared minus 2AD. And I still haven't gotten VI by itself. I need to undo that square over there. I'm going to square root both sides of the equation, which gets me VI equals the square root of VF squared minus 2AD. And there we go. I have expressed the initial velocity as a function of all other terms. Are you ready for another? Let's try it. Here's example 3. I've got the displacement acceleration equation, which is displacement equals the initial velocity multiplied by the time plus 1/2 the acceleration times the time squared. And then I also have a definition of the displacement, which is your final position minus your initial position. And your task is to express the initial velocity, or V0, as a function of the final position, the initial position, acceleration, and the change in time. Okay, pause the video, ready, set, go. Okay, let's do this. I am trying to get the initial velocity by itself. That means maybe the first thing I should do is get this term to the other side of the equation. So let's end up with V0 times delta t on one side. I'm going to have a delta x minus 1/2 a delta t squared. Now I'm going to put parentheses around delta t because sometimes I get confused and think it's two variables. So I'm going to put that there when it's next to other variables as multiplication so I don't get confused. Okay, I don't have V0 quite yet, so let's multiply both sides by delta t, like that, which lets me cancel. And I need to divide this entire side of the equation by delta t. And that's going to give me V0 on one side, delta x minus 1/2 a delta t squared over delta t. Now it seems like I'm done because I have V0, my unknown of interest, over here on the left-hand side, but I've also got this hanging out on the right-hand side, which I can substitute for. Remember, we are looking not for delta x on the right-hand side. We're pretending that's not known yet, but we do know the final position and the initial position. So all I need to do is actually just substitute in the definition of displacement in for delta x. And I can get my final value. Initial velocity equals final position minus initial position minus this term 1/2 a t squared all over delta t. And as a quick sanity check, is this the unknown I'm looking for? Yes, it is. Is everything on the right-hand side known? It is. Okay? At least in terms of how the problem was defined. So this is the way that we would symbolically set up our equation. And this, again, tells us some very important things. Before we even go to any numbers at all, we can see that if the difference between my two positions is big, then I must have had a higher initial velocity. And if it takes me a lot longer to do this acceleration, then I must have had a lower initial velocity. So this is great that it tells us these relationships between variables before we even get to any numbers. And if we did have numbers, if we did have knowns, this would be the point at which we substitute them in. Let's try a couple more. Here is example 4. I have the energy equations. Mechanical energy, the total mechanical energy, is the sum of the gravitational potential energy and the kinetic energy. And each of those terms is defined for you over there on the right. Gravitational potential energy is the sum of mass times g, which little g is 9.8 meters per second squared, the acceleration due to gravity, and h, the height. And then kinetic energy is 1/2 mv squared, the mass times the velocity squared. Your task, find velocity as a function of height, assuming all other variables are known constants. Ready, set, go. Okay, here we go. The easiest way to get the GP and the KE into the same equation is to just plug them into the definition of mechanical energy, which is our first equation here. So I'm just going to substitute in these values. The total mechanical energy is the definition of GP, mgh, plus the kinetic energy, which is 1/2 mv squared. And now I have velocity and height in the same equation, which means it's possible for me to now manipulate this using algebra and end up with velocity on one side and everything else on the other. So let's see what we have to do. First thing is to get v by itself. Let's get rid of this term over here. So I'm going to have me minus mgh equals 1/2 mass times velocity squared. Okay, getting there, getting there. I still need to get v by itself. Let's multiply through by 2 because I want to get rid of this 1/2. So let's multiply both sides by 2. That's great. So that's going to let me cancel these. And I'm also going to want to divide both sides by mass to get rid of those. So let's divide by mass. That's a little bit messy because of all my crossing out. So let's write it cleanly. I have v squared on one side. I just moved it over to the left-hand side because that's where I want it. And I have 2 times the mechanical energy minus mgh divided by the mass. Okay, I'm almost there. I'm almost there. I still need to get the velocity by itself, which at this point is just one last step. Let's take the square root of both sides. And if I do that, I get v equals the square root of 2 times the quantity me minus mgh over the mass of the object. So let me ask myself, am I done? Do I have the unknown of interest on this side? Yes, I do. The unknown is on the left side. And everything over here on the right-hand side was defined as known, which is great. So once I have this, I can tell a lot about how the velocity relates to these other variables. I can tell the greater my total mechanical energy at the very beginning, the greater my velocity at any point is going to be. That makes sense. The more energy I have available, the more could be used on velocity at any time. I see that height is on the top of this fraction, but it also has a negative sign in front of it. So that means the lower my height, the greater my velocity. And that also makes sense. As something drops down a hill or drops from a height, it's trading its potential energy for kinetic energy. So it makes sense that it would be reducing its height as it falls and getting faster and faster and faster over here with the velocity. And now as a bit of an exercise, a thought experiment to yourself, think about the effect of little g and mass on the velocity. And little g, if you remember from physics class, is defined as 9.81 meters per second squared for Earth. It is the acceleration due to gravity at Earth's surface but it could go up or down depending on where you are in a gravitational field. If we were on the moon, for example, g might only be 1.6 or 1.7 meters per second squared. And think about what effect does that have on the overall or the velocity of an object at some point. And also think about the relationship with the mass. It's not immediately clear what happens with the mass because we have it in two places in this equation. But again, a little experiment. Think up some reasonable values for these terms and see what happens when you change the mass. It can be quite interesting to play with the relationship between variables in this way. Okay, here's one last one on your own, example 5. The period of a pendulum, of a simple pendulum, is equal to 2 pi times the square root of L over G. And your task is to express the pendulum variables as a function of known constants only. And known constants is going to mean G and pi. Those are values that are defined. Again, G is 9.81 meters per second squared for Earth's surface, and pi is roughly 3.14. It's just a mathematical constant that happens to show up in the universe quite often. T and L, T is the period of the pendulum, and L is the length of the pendulum, are things that vary based on the pendulum itself. So let's see if we can do this example. Ready, set, go. Okay, let's try it ourselves. I'm going to just write the equation again down here so that I have it. L over G. It's easy for me to see. I want to get T and L on the left-hand side, and I want to get everything else, just pi and G and 2, which are all known constants, on the right-hand side. So let's get this L out of the square root, and I'm going to do that by squaring the entire equation. Let's square the whole thing. So I'm going to do squared, this thing is going to be squared, and the radical is going to be squared. That removes the radical. So now I have t squared equals 4 pi squared. I have to distribute the squared, both the 2 and the pi, and I'm going to get L over G out of the square root. Okay, that's progress. Let's get L over to the other side, which should be easy, because now it's just on the top over here. I can simplify this and say 4 pi over G times L, if that makes it a little bit clearer what's going on. L now has just a constant in front of it. And this alone right here, even if we paused at this step, this tells us something very important, that the period is related to just a constant times the string length for a simple pendulum, which is pretty cool. That the time it takes for a pendulum to swing back and forth depends only on the length, at least for fairly simple pendulums. But we're not done yet. We need to get only known constants on the right-hand side. So let's take one last step and put L on the other side. I'm going to divide both sides by L, and I would get t squared over L equals 4 pi, oh, I'm sorry, I forgot the squared here. My mistake, there's a squared. 4 pi squared over G, which is really cool. So on this side, I have pendulum unknowns, or pendulum parameters. And on this side, I have only known constants, which is really cool. And this is going to become important when we study empirical laws in nature. On the right-hand side, I'm saying that these variables of an actual real physical system, the period and the length of the pendulum, whatever they are, if I square the period and divide by the length, I'm always going to get the same number. The exact same value is going to come out. It's going to be 4 times pi squared over the local gravitational constant, the local acceleration due to gravity, which is really, really cool. And that's going to tell us very fundamental things about nature, as we will see in class. Okay, so at this point, you should be able to solve a physics problem using a symbolic solution procedure and derive functions of unknown variables in terms of known variables and constants. And remember, that's going to mean on the left-hand side, we have our unknowns. And on the right-hand side, we're going to have all knowns and constants. Nothing else. Okay?